Right, I'm recording now. I just had a battle with the thing not wanting to record. The other thing is I've just sat and written out all of these slides, videoed them all. Unfortunately, didn't have the camera pointing in the right position, so that everything I was writing was off screen. But the notes themselves are still good, so I'm going to use them, but instead of writing it as I video, I'm just going to sort of point my way through it. So, first of all, we have our original circuit, a series circuit, inductor of 0.1 Henry, resistance of 20 ohms, a 100 volt AC 1500 Hertz supply, with a common current through them all because it's a series circuit. And the first thing we're asked to do is find what value of capacitor would make that resonant at 1500 Hertz. Well, if we take a normal frequency of resonant circuit for a series circuit, we normally say it's equal to 1 over 2 pi root LC. So we need to rearrange this in terms of C. And a small amount of rearrangement, this is one way of putting it. I could have put F0 into the bracket and then not had a separate square on it. But effectively C is equal to 1 over the square of 2 pi and the square of F0, 1500, times L. We put our figures into that, 2 pi all squared times 1500 squared times 0.1. The reciprocal of that gives us 112.6 times 10 to the minus 9, or 112.6 nanofarads. So 112.6 times 10 to the minus 9 farads. I'll put an F on there really. Trying to work through the camera now, there's a bit of a lag. Okay, just as a check on that, I want to make sure that I haven't made a mistake there. I'll try and stop this camera from shaking on its arm as well. I'm going to put the figures back into the standard equation, so F0 is equal to 1 over 2 pi root L, which was 0.1, and C 112.6 times 10 to the minus 9, and that comes out of 1499.9 Hertz to one decimal place, which is approximately equal to the 1500 Hertz we started with, which confirms that we've not made a mistake. The purpose of this circuit is a band pass filter. If we look at a frequency response curve, V out on the y-axis against the frequency on the x-axis, we would have a curve something like this, where the maximum output on the 20 ohm resistor was at its peak at the frequency of F0, in our case 1500 Hertz. To find the actual potential difference across the components, we need to find the current, and I is equal to V over Z. But we could say that's equal to R squared plus XL minus XC squared. I really ought to modify that a little bit. I should make it XL minus XC all squared is probably the more standard way of showing that. When XL equals XC, obviously that just becomes R squared, and square root of R squared is equal to R, so our current is just going to be V over R. We have a 100 volt supply and a 20 ohm resistor, so that's 5 amps. So the potential difference across the components, all the potential difference will be seen across the resistor. From the supply, that is. The reactive components will have a completely different voltage across them. They will be equal to V equals I times, here we are, somewhere down here, times XC or XL. So XL, first of all we need to calculate the values of XL and XC. XL is equal to 2 pi FL, 2 times pi times 1500 times 0.1 Henry, and that comes out as 942.5 ohms approximately. I'm rounding the figures a little here, so there's small errors in it at resonance. XC should come out the same figure, we'll just put it in and make sure, that's a double check, 1 over 2 pi FC, 1 over 2 times pi times 1500 times 112.6 times 10 to the minus 9 farads. And that comes out as 942.5 ohms of reactance as well, which there's been an ohm sign on the end of there. So that the fact that they've come out the same suggests that we've made a double check and it's okay. Okay, the PD across the inductors then. Well, we just put our current, V equals I times R, or V equals I times X, L, or C in this case. 5 amps times 942.5 ohms comes out at 4,712 volts. It's the same reactance on both components, so it'll be the same across the capacitor as it is across the inductor. So we have a 100 volt supply, but our Q factor, that's the amplifying factor, how much higher the voltage is across the reactive components compared to the voltage from the supply, is equal to the voltage on the reactive component. In our case we'll use XL divided by the supply volts V. So we had 471.2, is that correct? No, 4,712, that little dot there shouldn't be there, divided by 100 is 47.12 ohms. That's our Q factor. There's no resonant, no unit for Q factor, it's just a ratio. Then we're asked to put the circuit in complex notation, and it's very similar circuit to as we had before. The layout's the same. The only difference is, I'm trying to stop the camera from shaking, is we're going to display not the capacitance but the capacitive reactance. And if you remember from work we've done before, the inductor has a positive value of reactance, 942.5 ohms. The capacitor has a negative value as well of the same size, minus J, 942.5 ohms. And of course the resistor is still just 20 ohms. Phasor diagram, it's difficult to do one of these to scale because the resistor is only 20 ohms against 942 on each of these scales, so I just had to cut the scale short. And obviously the normal method is to draw one phasor onto the end of the other phasor. So if I draw a phasor going this way, representing the minus XC, from the top of the plus XL, the two will cancel out to 0. And we'll just remain with R. So we could show this is our circuit where we're using the reference is the current because it's common to all the components in the series circuit, and our value of resistance, which is an in-phase component, in phase with the voltage and the current, is our R value. That's all we've got left in the circuit.